Now let's learn about Hess's law. This is a very neat law that allows us to solve for delta H for reactions for something that we can't find experimentally. So what we're going to do is focus on defining and using Hess's law. We're going to be calculating the change in enthalpy if a reaction is reversed, multiplied, or divided by a number. We're going to then combine reactions to get a desired reaction and determine the enthalpy of the final reaction based on those components. And that will all make a lot more sense once we actually do it. So Hess's law is a law that allows us to add multiple reactions to solve for a final reaction. If we think about why this is, it's because delta H is a state function. So let's remember what a state function is. In a state function, it does not matter how you get from one place to another, just that you do. So let's say that we have a reaction that comes and goes from one energy to another. Here it's going to be denoted by these lines. And the delta H3. From an energy standpoint, it does not matter how you go from one line to another. It doesn't matter if you go straight there, as we have in the blue arrow, or if maybe we have two reactions, where first we have a reaction that brings it up in energy, and then we have a reaction that brings it down in energy. We're still going from the middle line to the bottom line. Now, of course, we might say, but that's a different set of reactions. And you're right, it is. It's just that from an energy standpoint, it doesn't make a difference. From a mechanistic standpoint, and you don't know what that means yet because you're going to learn about it in later class, but then it would make a difference. But from a pure energy standpoint, it doesn't matter. It doesn't matter if these reactions actually happen in these order. All that matters is that if you add the reactions up, you get the final reaction. So how do we actually do these? Let's take a really conceptualized general example that's simple, and then we're going to add some complexity to it, and then we'll do an actual reaction. So for our generic reaction, let's say that we have this reaction, this A plus 2B goes to 2D, but let's say that there's no way to experimentally determine it. But what if we can experimentally determine these two other reactions? The A plus 2B goes to C, and the C goes to 2D. If those are experimentally determinable, what happens when we add them up? Well, the C's would cancel. And if those C's cancel, now we have A plus 2B goes to 2D, which is our final reaction that we were looking for. What Hess's law allows us to do, and this slide is sort of the encompassing what Hess's law really is to be able to just add H1 and H2. So we're able to take these two reactions that add up to be our final reaction to get our new enthalpy. Now, we may have to alter these a little bit. Of course, sometimes we're going to have an enthalpy for a reaction and it won't quite add to the reaction we want. But if we manipulated it, maybe if we reverse it, or maybe if we multiply it by 2, or multiply it by 4, or divide it by 2, maybe then we would be able to add it to be our final desired reaction. We can still use Hess's law for this. We just need to change the delta H appropriately. Because if you have 2 times the amount of the species, you're going to have a different delta H. If you reverse the reaction, you're going to have a different delta H. So let's talk about each of these now. If we need to multiply a reaction, then we're also going to multiply the delta H. So let's take this example. If we have these two reactions and we want to get our final reaction, take a minute and look at this before moving on. Now we'd like to solve for the final reaction here, but if we just add them up like we did on the last slide, we're not going to have 2Ds and our C's aren't going to cancel. So what we need to do is we need to multiply the second reaction. The C goes to D. We need to multiply that by 2. If we do that, now our C's will cancel. Now, look at our original rule that when multiplying an equation, we multiply the delta H. Since we multiplied the equation by 2, we need to multiply the delta H by 2 as well. So instead of 150 kilojoules per mole, it's 300 kilojoules per mole. Once we make it to this step, you'll see that we're back to exactly what we did on the last slide, where we have A plus 2B goes to 2D. We added to our final reaction, we add our delta H's. So now we simply add up our 100 and our 300 to get 400 kilojoules per mole. This same rule works if you divide. So if you divided by 2, you would simply divide your delta H by 2. And of course, it would work with multiplying it by any other number. Even if you had something crazy like 1,000, you would just multiply your delta H by 1,000. Now let's talk about what happens if you reverse the reaction. So take a second and again, look at our setup here. We have the two reactions that I've given you the delta H for. We want to calculate the delta H for the last reaction. When you need to flip a reaction as you do here you would need to flip the C and the 2D. You change the delta H to the opposite sign. And this makes sense based on all of our other work that we've done, right? It's products minus reactants to find our delta H's. So if you switch the products and the reactants, it's just going to be the negative. So if we reverse this reaction, now our C's will cancel. We'll get our A plus 2B goes to 2D that we wanted. And we just have to reverse the delta H of the second reaction. From here, we do the exact same thing that we did in the previous slides. We added up our reactions, we add up our delta H's, and we get, in this case, 100 minus 250, or 100 plus negative 250, whichever you want to think of it, to give us our negative 150 kilojoules per mole. Now let's do an example with actual chemicals. Before, we've just been doing it generic so you can learn the rules. So let's say that we want to know the enthalpy of the reaction that's shown here. But for whatever reason, we can't measure it directly. Now let's say we can measure these two directly. We know these two enthalpies. I've given them to you. So perhaps we can use Hess's law to solve for our final enthalpy. Before we move on, you have all the tools you need to be able to solve this problem. So try solving it on your own first, and then press play when you either get stuck or get it solved. So the first reaction is looking pretty helpful. Our reactants are correct. Now we do have a product that is not in our final reaction, so we're going to need to make sure that that cancels out by the end. If we look at our second reaction, we can see that we actually have one of our desired products. So look at that a second. If you look at your second reaction, you have a desired product, but it's in your reactant side. So we're probably going to need to reverse that. So let's go ahead and do that. Let's take this and we're going to flip-flop the reaction. Now when we do that, when we reverse the reaction, we change the sign of the delta H. So now the sign is negative. So from here, we can see that our SO2 cancels. And we now have all of our reactants and all of our products and nothing extra. Now, if you need to, and you didn't get this on your own the first time, take a moment and sort all of these out for yourself. Make sure that you can see where the S comes from, where the 3/2 O2 come from. Because that one's a little tricky because you have 1 in the first reaction and a 1/2 in the second reaction, and where your SO3 comes from. Since our reactions are going to add to be our final, so will our enthalpies. So we can add up our enthalpies to get our final enthalpy. Just be careful that you add in your changed enthalpy, because here you did have to make that delta H a negative. So make sure when you add your enthalpies up, you keep that negative. Then it becomes a matter of typing it into your calculator, and you get negative 395.4 kilojoules per mole. We're going to do one more example, but this one's a little extra complicated, and I've decided to put it in its own video. So stay tuned for the video with a much more complicated example. In this one, we only had to do one manipulation, but you might have to do several manipulations to get to your final reaction. So keep that in mind and stay tuned to see how to do this in the next video. So as our quick review and sum up, delta H can be determined if you have component reactions which add to a final reaction. Whenever you have this, you can sum the enthalpies of the component reactions to get the final. If you reverse a reaction to be able to do this, you change the sign. If you multiply or divide a reaction in order to do this, you're going to multiply or divide the delta H by the same number that you multiplied or divided their reaction by.